guys, today we're going to do 2-5 complex zeros and the fundamental theorem of algebra. Our objective will be to learn about the two major theorems and complex conjugate zeros. So our two major theorems. First, we have the fundamental theorem of algebra. And the fundamental theorem of algebra states that a polynomial function of degree n has n complex zeros, real and non-real. So some of these zeros may be repeated, some of them are real, some of them are not real. So fundamental theorem of algebra. Linear factorization theorem. If f of x is a polynomial function of degree n greater than 0, then f of x has precisely n linear factors. So if the degree is greater than 0, that's how many linear factors we have, where a is our leading coefficient of f of x, and z1, z2, z3, all the way down to zn are the complex zeros of f of x. So z1 are not necessarily distinct numbers, but like we said before, some of our zeros may be repeated. If we want to write the polynomial function in standard form, we need to FOIL, and standard form means our exponents go from highest to lowest. So when I FOIL this, I get x squared plus 2ix minus 2ix minus 4i squared. 2ix minus 2ix cancel each other out. That's why we are conjugates. Negative 4i squared. I squared we replace with negative 1. Therefore, negative 4 times negative 1 is plus 4. So f of x is equal to x squared plus 4. Once again, I'm going to multiply the conjugates first so that we can cancel our imaginary parts. So I'm going to multiply x times x to get x squared plus x times the square root of 2i minus x times the square root of 2i minus square root of 2 times the square root of 2 is 2i squared. X square root 2i cancel. 2 times I squared, this I squared turns to negative 1. So we have x squared plus 2 times x minus 5. Now we FOIL again, x cubed plus 2x minus 5x squared minus 10. I have to write in standard form, therefore f of x is equal to x cubed minus 5x squared plus 2x minus 10. Once again, conjugates, x squared minus xi plus xi minus I squared x squared minus 6x plus 9. And now I multiply x squared plus 1 times x squared minus 6x plus 9. X times x, x squared times x squared is x to the 4th minus 6x cubed plus 9x squared plus x squared minus 6x plus 9. Simplify. F of x is equal to x to the 4th minus 6x cubed plus 10x squared minus 6x plus 9. in order to identify the zeros and the x-intercepts of our graph, we need to take our factored form, set each factor equal to 0, and solve for x. So I would take x minus 2i equals 0, x equals 2i, x plus 2i equals 0, x equals negative 2i. So we have two zeros at x equals 2i and x equals negative 2i. But our zeros are not real because we have I in it, which is imaginary, and that means our graph has no x-intercepts. Here we get x equals 5, x equals square root of 2i, x equals negative square root of 2i. Are our zeros? We have 3 zeros because it is a cubic function. Then only 5 is our x-intercept because 5 is our only real zero. So that's the only place we'll actually intercept the x-axis. Then in our quartic function, which means we have a power of 4, we get x equals 3, x equals 3, x equals I, and x equals negative I. There are 3 distinct zeros. 1 repeats, so we have a multiplicity of 2 at x equals 3, meaning that x equals 3 occurs twice. And due to this multiplicity, we only touch the x-axis at 3. Write the polynomial in standard form and identify the zeros of the function and the x-intercept. So I'm going to take x minus 3, I, set it equal to 0. X plus 3i, set it equal to 0. And solve for x. We get 3i, and x equals negative 3i. These are our zeros. We have no x-intercepts. We have no x-intercepts because we only have imaginary zeros. And standard form would be x squared minus 3xi plus 3xi minus 9i squared and our function would be equal to x squared plus 9. If I needed to simplify a radical in my denominator, for example, 2x divided by 4 minus the square root of 3, I would multiply my numerator and denominator by the conjugate. The conjugate would be 4 plus the square root of 3. So when I multiply that out, I get 16 plus 4 root 3 minus 4 root 3 minus 3 all over, 2x times 4 plus root 3 in my numerator. My root 3's cancel. I get 16 minus 3, which is 13, and I could distribute in my numerator to get 8x plus 2x root 3. As you can now see in my simplified answer, I no longer have a radical in my denominator. So when I multiply by the conjugate, it gets rid of the radical. The complex conjugate zeros theorem states if you have a polynomial f of x with real coefficients, if a and b are real numbers with b not equal to 0 and a plus bi is a 0 of f of x, then its complex conjugate, a minus bi, is also a 0 of f of x. So if you have one imaginary number, then you could also have the other conjugate of that. So if we have a polynomial with real coefficients whose zeros are negative 3, 4, and 2 minus I. That means we could also have 2 plus I. And when we go to write our factors out, we have to do x minus the 0. So we would do x minus negative 3, which turns into x plus 3, x minus 4, which turns into x minus 4, x minus 2 minus I, and x minus 2 plus I. And then we multiply them out. And then we multiply again. Combine like terms. Would be our polynomial. You guys try this one. Write a polynomial function in standard form with real coefficients whose zeros include x equals 1, x equals 1 plus 2i, and 1 minus 2i. So we have to remember we could also have 1 minus 2i. We could also have 1 plus I. So you guys go ahead and multiply that out.